Okay, we'll make a start then. Welcome everyone. Thank you for choosing to be here for the last part of a very hot day, especially over what will almost certainly be two more interesting talks. The token slide about me. I'm Will. Started a company called Insecurity in 2018, doing pen testing and training. My background started in digital forensics in 2008, straight out of uni. Defected to the dark side of hacking in 2014. I've been breaking things since. I've been very lucky and humbled to have sort of spoken or trained at a lot of places. This talk is about passwords. You might have even already guessed by the hashcat symbol here. And I'm also part of the DEF CON Password Village. So if anyone happens to be out in Vegas in a few weeks, swing by and say hi. But yeah, without further ado, let's jump into the agenda, because we're going on a bit of a whirlwind talk through a number of things. We're going to go into some slightly deeper, sort of more unorthodox and creative password attacks. We are then going to jump into weird and wonderful things in data breaches, and then into foreign language and Unicode and emojis, and wrap up with a tool to help automate some of the heavy lifting for those of you who are. Have we got any pen testers in the room, red teamers? Enthusiasts, password crackers? Okay, fantastic. Okay. We're not really going to do like the 101, how to crack a password. We're going to give a bit of assumed knowledge, but of course happy to field any questions at the end. So we'll start straight on with passphrases. Because, you know, as NIST published in SP 863B, really, really boring dry read. You'd need a lot of alcohol to get through it. I don't encourage it. They do promote and encourage length over complexity, and people choosing passphrases over passwords, amongst other things. So, in a passphrase world, one of the basic ways, the most basic ways we can attack hashes in a passphrase is something like this. We're going to use not exclusively Hashcat. There are a couple of other tools, and you're going to notice Hashcat's probably going to be following us around the screen. But most of the tools and things, most of the techniques that are being demonstrated will involve Hashcat. So, A1, attack mode. 1 is combinator mode. Take your two word lists, feed it to Hashcat. Fine. You can get two-element passphrases. And when I say element, I'm referring to sort of QWERTY, and then 1, 2, 3, 4, 5, 6 would be a two-element passphrase. Sometimes you hear words or passwords itself, but we're going to stick to the word element. Okay, fine. But what about delimiters? Delimiters are becoming more common, and although they will, and always do, make your password substantially stronger and more resilient to attack, attackers also, of course, do know this, and we can start to attack passwords with delimiters. The most common one you generally see is a space. And one of the easiest ways we can emulate this is to, again, use our attack mode 1 combinator and use -J. So we've got -J and K, which allow you to effectively insert a single rule to the right or left word list. $1 is append. In this case, we're appending a space. So what that is doing is taking every candidate in our first 100 TXT, forcefully inserting a space, and then appending the second top 100 TXT in this instance. And as you can see, we get stuff like this. Element, space, element. Okay? All good so far. But now, we can actually run full rule sets. One of the disadvantages of a raw A1 attack mode is that you can't append -R and take on your rules as you normally would. But if we can take our output from standard out, type it into Hashcat, we're now back into our Hashcat kind of safe environment. So you can then, do your attack, your Hashcat attack strings as usual, and then whatever rules you want. If you're remiss of me not to mention one rule to rule them still here, because I generated one rule to rule them all in 2017 for a former company, and it was getting a bit stale. I was very humbled that it was widely accepted by the community, but it was getting a bit stale, and I had a few people saying, when's the next one? So I finally got to work, and it was a couple of years ago now, reinvigorated it. It's a performance update, so on the data breaches tested, I managed to get about 5%, it's a little bit more now, 5% drop in rule numbers for 0% performance loss. So it's the same set, but it's just a bit more efficient now, it's a bit more tweaked. And there's a company blog post there if you're interested. But we don't want to talk about two-element passphrases, we want to talk about 3 and 4 and onwards and upwards. So, we have other tools that we can use to aid us on our quest. The first one being Prince Processor, which is a standalone tool. Doesn't come with Hashcat, has its own GitHub, but it's a candidate generation tool. And what Prince will do is it will take one word list, and then depending on the configuration you give it, it will allow you to mutate that word list into multiple passphrases. So in this instance, we're calling Prince, and we are saying we want a minimum element count of 3 and a maximum element count of 4. So Prince will go through the word list you give it. Rock use a common one that people like to use. and it will extrapolate individual candidates from that word list with a minimum of 3 elements, maximum of 4. In this case, you're also saying we want a minimum overall length of 8. And we often do that, especially for the pen testers who often do AD dumps and things, because NT is so fast, we can exhaust an 8-character key space fairly trivially with modern hardware. We can then pipe that to hashcat and then business as usual. Okay? Fine. But there are also other things we can do. For example, we can introduce delimited lists. Now, I'm going to introduce another tool called Combinator X in a second, and there are some pros and cons to using these. With print, it's a little bit more rigid because we have to already have a pre-processed word list in order to do this. So the top 100 space here, as kind of implied, would be a word list that I've sort of pre-forcefully added a space to the end of each line. So there's a trailing space at the end of each line. Now, that's fine. We can take 3 or 4 elements from this, but there will be a trailing space on that last candidate, whatever it is. So what we can do to delete that last trailing space is -J, close square bracket, which is effectively truncate the last character, therefore getting rid of that trailing space and giving you passwords like this. And I should say that none of these passwords are synthetic. They all come from either live, like real sort of past data breaches, or from the Have I Been Pwned, which is, of course, a conglomeration sort of all the data breaches that Troy Hunt has anyway. So nothing's kind of been sort of pre-generated. Okay, Combinator X. So this is a slightly lesser known tool. Comes with hashcat utils. So it is there, whether you realise it or not. And this allows you to do sort of things like this. We can take a couple of word lists. We've got 3 in this instance. We can call Combinator X, tacking on our 3 word lists with -1, 2, and 3. But it gives us a great deal more flexibility when it comes to inserting delimiters. Because as you can see down the bottom here, we can have a separator 1 and 2, and even though I've inserted spaces, you can make the first one a comma and the second one a colon, or whatever you want. And you don't have that pre-delimited word list requirement beforehand. Again, there are sort of pros and cons to this. Print processor has a maximum password length of 16 overall. To be honest with you, you can just edit that in the C file and recompile to get some better mileage if you want. But out of the box, we've got 16. But yeah, as you can see here, it will take elements from 1, 2, and 3 and combine them in the order you give it. Of course, if you have 3 different word lists, you will never ever see elements from word list 1 in positions 2 or 3. Whereas with prints, as it's pulling from a single word list, you could. And another thing to note with Combinator X is it only accepts the same word list twice. So if you try and give it a third time, it'll say no. So just copy-paste the word list and then rename it. Just because, I was scratching my head about that to begin with. But different tools for different jobs, I suppose. But building this into a kind of a more of an attack flow, we can see here, as previously spotted, we have our Combinator X with our separators, and then we can pipe that into hashcat, and it's business as usual in terms of the hashes we're cracking. Case toggling. Okay, so this is an interesting one. We're humans, and password security, like cybersecurity overall, is a people problem, not a technical one. And we love to capitalise the first letters of our passwords. We always have. Just like we've always been conditioned into adding a number and a special character to the end of our passwords. Statistically speaking, the number 1, as you can imagine, is the most popular. And also, the exclamation mark is the most popular character. Not only because we love to exclaim our passwords as humans, but we're also creatures of habit. We're very lazy. And the exclamation mark is on the same physical key as 1. So 1, shift 1, is a lot easier than me dragging my hand across a keyboard to find an asterisk or a space. So as you can imagine, 1, 1, 2, 1, 2, 3, 1, 2, 3, bang, etc. Very, very common. Just like capitalising the first element in passphrases, where people are using passphrases. So in this example, I like to draw reference to the wiki, because I've been guilty of this for years. No one really reads it, not nearly enough as they should, and there's an absolute goldmine of information there, and the E and 3 rules can really address this kind of thing. So in the first example, the colon is a pass-through, so test the vanilla candidate. We're testing a completely random password, and then running the 3 rule in position 0, 1, and 2, you can see we're capitalising 0, 1, and 2. Simple. The E rule at the bottom will look for that space delimiter and then capitalise everything in one go. For such a simple and single rule modification, make sure it's in your rule files. You might miss some things otherwise. Yanis, who's part of Team Hashcat, goes by Toxic online. Hope for Toxic 3 rule. It's been default with Hashcat for a long time and does address a lot of this already. So if you're not already using it, consider using it. So, building that back into our attack flow here, we're using Combinator X again, but you could use prints. construct your word lists, construct your elements and delimiters therein, depending on what you're trying to attack. Bolt on a rule, and then you can get some other things where you can sometimes get capitalizations and things that you otherwise wouldn't have got. Engrams. Okay, something that, again, that's kind of grossly underlooked, I think. It's been around for a while, but people really aren't addressing it. We've got our textbook Wikipedia reference at the top. We're using SteelCon as an awesome conference. You can see when we are looking at this in a 2 gram and a 3 gram phrasing, shall we say, what we're doing here. We're taking individual elements, so SteelCon is an awesome, so on and so forth. Now, that's great, and this is good especially for very large texts. If you're doing target-specific attacking for a given data breach, maybe it's a gaming-related data breach, maybe you're targeting for movie and film characters, books, poets, whatever it might be, large texts can be fantastic for doing this kind of thing. And you can also use K and C grams, which are character grams and character set grams, respectively. So you can actually start splicing up the letters and roll them along, and it becomes really, really powerful. There's probably more than this. There are 2 tools, Fraser and Gramify, that I came across, but I do have to give a shout out to Gramify. I know the guy who wrote this. It's more modern. It's, in my opinion, a bit more powerful. It's definitely kept more up to date. So, when using big texts, let's do an example. This is from the Have I Been Pwned hash list. So I took the Bible and the Quran, both in Arabic and in English, ran that against Have I Been Pwned in 2 through 6 gram stages, both the vanilla candidates and using Toxic's rule. And you can actually see, first of all, how many people use phrases from the Bible and Quran in their password, clearly. But second of all, applying rules, how many people do things like capitalisation and things. So if you're not looking at using these rules already in your attack flows, you could be missing out on these on further elusive planes. We'll touch on more on this later, but you can crack native Unicode characters as well. Anything that falls outside of ASCII or has a colon in the password, Hashcat will by default hex encode that, but you can attack it in native Unicode as well. Okay, another interesting attack, which is pretty useful sometimes, especially on large hash lists. After a fast run, my definition of a fast run is rock your one rule to rule still. Great, fine, done. You've cracked a load of passwords. Take those passwords, and in this example we're using the Gamigo data breach. It was a gaming website that was popped in 2016, I believe. So I've taken those passwords, I've then remangled them with one rule to rule them still, and I've created a word list here. Gamigo, one rule, and then the planes that I've got. We then strip out all the digits and punctuation, strip out all the alpha characters to create an alpha and a non-alpha list. Smash those two together in an attack 1. Combinator mode, and you'd be amazed at some of the weird and wonderful cracks you can get out of it. So this could all be sort of, scripted and done, but it's just one more thing that you can use. This has better mileage when you've already got a substantial number of founds already. If you've got a substantial number of founds from multiple cracking sessions, this will work more. The more data, the better, obviously. But you will be surprised at what you can get. Okay, intermediate scaling masks. This is a bit of a weird one. Scratching my head about this for a while. Bit of an edge case. I'm not saying, especially not in a pen testing perspective, you wouldn't know this. But let's say you know the start and end of the password, but you don't know the middle. Let's say it starts with a number, ends in a special character. There's lowercase alpha in the middle, but you don't know how many. What can you do? Because that's actually quite a tricky thing to do natively in Hashcat. You can't just use an incrementing mask, even with custom character sets. You'll end up with a lot of redundancy, and we want to optimise our attacks to reduce the key space as much as possible. So, what we can do, and this is the password, crap, is we can emulate that in one of 2 ways. Potentially more. There are plenty of people who know a lot more than me. But we can either use attack mode 6, which is a hybrid list plus mask, or attack mode 3, which is raw brute force. And you can hopefully see from the colour coding what we've done here. Stick your numeric decimal character in a word list, then incrementally build up your lower alphas, part that to standard out, then push that back into Hashcat, and then use a rule file for your final special character. That will do it fine. You can get exactly the same impact here, exactly the same effect in attack mode 3, starting with our decimal, setting a minimum increment to 2, optionally if you wanted to start from here, and again tacking on the rule at the end. But there is actually one big difference here in terms of your mileage. The buffer used in a hybrid A6 mode is a 32-bit integer, whereas the attack mode 3 is a 64-bit integer. So you're going to hit an overflow much, much quicker using attack mode 6, which is why it's generally preferable to use attack mode 3. Because sometimes you're asking, oh, how many L's do I have? You'll run out pretty quickly. If you're doing question mark A and a brute force above 9, you're going to overflow. So don't try and sort of crack 20 character passwords. A, you're never going to do it anyway. B, it's computationally infeasible due to our integer limits. Okay, next, Markov chains. These are pretty cool. At least I think they're pretty cool. Let's say you want a targeted attack. I'm going to use a Minecraft data breach. I'm using the Lifeboat community, which was popped in 2016 or 17. Big Minecraft-orientated community, and loads of unsalted MD5s, perfect for this kind of stuff. It's reasonable to assume that if you've got a breach and you've got 5 million Minecraft players, it's reasonable to assume that a lot of the passwords could be Minecraft-related. I mean, don't get me wrong, you're going to get your standard stuff in there, but I think that's fair to assume. So maybe we want some Minecraft-related passwords to attack. Now, by default, if anyone's come across Markov modelling, it's the statistical probability of a character based on its previous position and where it is in the password. So, for example, if a password starts with Q, it could be fairly reasonable to assume the next letter might be U. And there's lots of statistical analysis done on cracked passwords showing which character is the most common first character, when that character is selected, which character is the most common second character, so on and so forth. Now, these are called Markov models. Now, by default, Hashcat uses RockQ as its own inbuilt Markov model. So, RockQ, I've said this a few times now, I'm sure everyone's heard of it. It's a very small breach, about 14.5 million passwords in it, but it's the one that's been used over and over again throughout time. And Hashcat uses that for its internal Markov lookups. So when you're doing a brute force, like question mark A, multiple times, Hashcat doesn't go A, B, A, C. It doesn't build up incrementally. It's already giving you the best fighting chance of cracking that password based on the Markov selection of how people in that data breach selected their password. So it's already giving you that helping hand. But what if you want to change that model to a Minecraft one? What I did was I went online, went to a couple of wikis, downloaded every Minecraft object, skin, list, baddie, you name it. My kids at the front here could tell me more. I'm not a Minecraft player. I downloaded that, mangled them with one rule, and created a word list full of a huge number of really crazy mangled passwords. Fine, good. The next two steps are just creating a Markov table in a Hashcat-compatible format. The binary there comes with Hashcat utils, and this is just compressing it. We don't need to worry about it. What's important is the actual attack. So I've now created a Minecraft Markov model that I want Hashcat to use in place of RockQ. We're doing that here. Standard 8-character raw brute force here. Passing my Markov model here this time. Business as usual. And what I found was after 60 minutes of runtime, I'd actually managed to crack 10,000 more passwords using my Minecraft Markov than if I'd let Hashcat run by itself. Now, ultimately, if you actually exhausted the word list, the ultimate number that would crack would be the same, of course. This isn't about cracking more passwords. This is about cracking more passwords in a quicker time before we, as really impatient, myself included, people, Control-C, because we take one look at that time to crack. And I'd like to say, if it says 6 weeks, but let's be honest, if it's anything more than 20 minutes, you'll always hit Control-C. I know you're nodding in the front. Yeah. We're such lazy creatures of habit. Let your attack cycles run, please. Okay, so yeah, getting those cracked faster. Hashes with hashes. Okay, dust to dust. Hash shucking. So this has been, again, around, I think, for a while. It blew my mind when I first heard about the ability to crack password hashes using password hashes. And this stems from something else. We're going to take a step out of our adversarial mindset for a second and think about if anyone here manages applications for users. Let's say you want to upgrade the security for your users in your app, because for 6 years now you've been using unsalted MD5s, which is bad, and we don't want that, and people need to upgrade to make sure they're using good, resilient cryptographic hashes. Common example, bcrypt. Very good, very strong, very resilient to attack. What options do we have? Right, do we just do a mass password reset? Yeah, could do that. I know a lot of users, but it happens. Do we update it on next login so that next time they log in, their new hash is then maintained in the database? Do we rehash the hash, which requires the original and the sort of secondary hash being stored? Now, there are some right ways and some wrong ways to do things. We can already model this and emulate this in Hashcat. For example, taking a vanilla MD5 and then decrypting it, as an example. We've got a Hashcat mode 25600 that can do that here. And you can, jump the slide. And we can see how we can take a vanilla candidate of insecurity and we can crack it when it's a nested MD5 and a bcrypt. Fine. There's a great talk by Sam Crowley, who goes by Chicken Man Online. He's one of the core developers of Hashcat, called What the Shark. It was from Deaf Gone Password Village. I think it's probably about 4 or 5 years old now. But he obviously does a really, really good job of digging into why this is a thing, how this is a thing, and how we can go about mitigating it. So let's actually have a look in a kind of like a visualization, because I think it's better to see this sort of thing in a picture. We've got a happy user up here on the top left with a clear text password as displayed. Now, that's not an uncrackable password by any means at all, but it's not a simple password either. It's got sufficient entropy to make that fairly okay. Our happy user here has used that password on site 1 and site 2. Site 1, as you can see, uses a vanilla SHA-256. Site 2, bcrypts that SHA-256. But oh no! The sites have been popped. Both of those databases are leaked. Not uncommon. The attacker now is in possession of the database from breach site 1 and breach site 2. Now, obviously, if they identify that there's an email address present in both, and they've cracked the SHA-256, they're going to try the password to see. Of course they are, clearly. This is where credential stuffing comes from. But they don't always have that. But what the attacker almost certainly will have is a huge list of uncracked SHA-256s, both from the breach there and from other breaches that use SHA-256. So what the attacker can try and do is to run those SHA-256s that they haven't cracked through bcrypt in the hope that they actually get a match. And if they do get a match, they know they've now got the password hash from breach site 2. Now, you might think, well, great, we still haven't cracked the hash. And this is not necessarily about cracking the hash at this point. What this is about is now being able to attack a SHA-256 rather than attack a bcrypt. Because now we're working in SHA-256 land, which is substantially quicker. I think these are based off an RTX 3080. Anyone who's tried cracking bcrypt knows that if it's not something ridiculously simple, you're giving up on it. You know, pen testers don't get out of bed for a few hundred or a few thousand guesses a second, and bcrypt is painfully slow for a reason. So if your password is either half decent, you're probably not going to get it in bcrypt. But SHA-256, yes, you've got a distinct possibility. Of course, the inner hash has to be faster than the outer hash, but more importantly, it needs to be unsalted. If the inner hash is unsalted, you can't do it. All bets are off. But it does allow you to then crack at faster speeds than C. And it's not just data breaches. This works in AD as well. I've got to not get too excited and run off on a rant here, because I could talk all day about the insecurities of Active Directory and Windows domains, but everything in terms of a credential, more or less, in Windows land under the hood is an NTLM hash. Some of you, in fact many of you, might be really, really excited to know that Microsoft, of course, has now formally announced the deprecation of NTLM. Hey! After Server 2025 and 24H2, you no longer have to worry about parse the hash. But what's the replacement? Kerberos. They've called it IA Kerb and local KDC, but it's Kerberos under the hood. And there's Kerberos relies on NTLM for pre-authentication timestamps and service tickets. Who knows what's going to happen there? I'm going to let Microsoft figure that out. But pen testers are going to have to work. They can't pass the hash, allegedly, after this comes out. So we'll have to see how it goes. Everything under the hood is NT. Save your uncracked NTLMs, and I'm not condoning or encouraging you to save client hashes for years. Don't do that. On big assessments, multi-domain trusts, if you've got uncracked NTs, you can use them to crack hashes that you might get from Responder, anything that you relay. And in Windows world, that's fine. Because if you can crack an NTLM v2 to get the NT, you can now pass the hash, business as usual. It's as good as knowing a password. Okay. Unicode. This is where it gets a bit more fun. And foreign language characters, and basically things that we often, assuming we're all using kind of, normal English QWERTY keyboards, things we don't often see. Now, we can absolutely do this, not just in Hashcat, in other tools too, but as you haven't already guessed, I'm a huge Hashcat fanboy, so that's what we're going to do there. In the example here, we're looking at a UTF code point table to look up. 600 to 6FF, for example, is Arabic. I think that's the second example here, start code point 600 to 6FF. So we're just printing out the respective characters from different Unicode character sets, including, of course, emojis. Now, this is pretty cool, because we can actually attack these. And I'll just draw attention to this here, because it'll be important in the next slide. When we attack in hashcat, we can often attack in hex. And we need to do a lookup for the hexadecimal representations of these Unicode characters. So this Arabic number sign, for example, is D880. That's 2 bytes of hex. Our ASCII is 1 byte that we use, but UTF-8 is up to 4 bytes. And if you go into Eastern languages, sort of Japanese, Chinese, Taiwan, sort of everything around there in emojis, we're into the 3 and 4 territory, which is actually really, really hard to crack because our buffer that we have, that I referred to earlier, will fill up really quickly when it takes multiple bytes to attack a single Unicode character. So, how can we do this? Well, we can actually pass native Unicode characters to standard in, and Hashcat will often accept that. But it's designed, it processes bytes, not passwords, so it's designed to do this. You passing hexadecimal. So what we've got here is we've got 4 custom character sets to attack emojis. But you'll notice here we've got custom character set 1 is just F0, then F9. That would represent the emojis here. So if we were attacking Arabic, we'd have the first hex character is always D8, for example, if it's D8. And you'd effectively make sure that those 4 character sets had every possible combination of hexadecimal UTF-8 bytes for you to attack your language choice. And then, after passing hex char set, very important, so Hashcat knows you are actually cracking in hex, you then apply a mask at the bottom. 1, 2, 3, 4, 4 times. So that would crack a 4 emoji password, for example. 1, 2, 3, 4 being a single emoji, because of the 4 hex bytes required. We can also do this in rules. Hashcat does accept it. You need to escape the hex, as you can see in the top part of the slide there. But you can append, you can prepend, you can do lots of fun things with emojis, and you can build those up as you want to do things like this and crack real passwords. These are real passwords from data breaches. People do use emojis in passwords, especially, we're living in an age of mobiles where people can create accounts for things on their mobile. We've all seen wireless SSIDs being broadcast with emojis in them, so, why not passwords too? So, yeah, people do use them, and everyone loves love hearts in password. It's like, in terms of genres, it's all about the love when it comes to passwords, which I suppose is a positive thing. But what you can then do is build on that. Download every word list dictionary you can find. Look through all your existing founds that you've got. Your pop file should be huge. Any pen test will have a huge Hashcat pop file by this point. Loop through everything you've got and extract out all the code points. And you can create word lists out of your existing founds and downloaded word lists to address these. And where any time you've got a Unicode character or a full word, you can start attacking these word lists to do things like this. Again, I've not pre-created this. These are real passwords that from my Unicode word lists I've cracked from a lot of the have been pwned. Some of them are data breaches outside of that. But again, these aren't things you'd find running RockQ and one rule to rule and still, put it that way. Now, I appreciate these passwords are probably out of what you typically find in an Active Directory dump, but we're not specifically talking about pen testing here. We're talking about wider password cracking. Okay. That looks like a pretty good password, right? Yeah? No? Hands up who thinks that's a pretty good password. By virtue of the fact that I've said that, people are now going to be tempted. And I can see people looking like sheepishly like, shall I? No? Yeah, we've got a 50-50. We've got some bold people, I admire that. Okay, so let's look at it. Let's deconstruct it. We've got 12 characters of that. Lower alpha, numbers. Okay, character set-wise, not fantastic. 12, okay, a bit better. But what if I was to tell you that number is about 2 months out of date now? That password appeared in 890 breaches in Have I Been Pwned. That seems like a disproportionately high number for what is seemingly a face-rolled password, right? And that's because that password is actually MySpace password when typed into a Zhuyin or FOMO keyboard layout, which is almost exclusively all of Taiwan and some surrounding places. And that is a terrible password. I mean, that's up there with 1, 2, 3, 4, 5, 6 or QWERTY. Very common, though, in Taiwan, for example. And you can see how these characters are then converted to their native Unicode and what they represent. Now, the transliterated password might be hashed. Big caveat there. I'm not going to say that you're always going to see this because you're not. It depends on how your keyboard is passing that data to the operating system, of course, or how it's being hashed in the database. But it often does get hashed that way. So yeah, it looks terrible, but it's actually not. And then if you dig deeper, you can start actually finding loads and loads of examples of these transliterated passwords because, not everyone types password using English letters that we all know. That's actually a thing. And you can see here how we've got the native word and the transliterated password, followed by the actual translation of what they mean, and the number of times they occurred in Have I Been Pwned, as of a couple of months ago. So those translate passwords look weird as hell, don't they? I mean, they're completely facial. You wouldn't expect to find them there. Now, Hashcat Legacy, which has been dead for a long time, does have a table lookup attack, which is attack mode 5. It is actually referenced in plenty of places if you're on the Hashcat forum or Discord. But this tool from the same guy who actually did the Ngram tool is updated it, and actually I feel a bit guilty because he very kindly created that out of a conversation I was having with him because I was struggling with Hashcat Legacy. So I created a load of table lookups and I needed something a bit more robust. And this tool's really, really good for doing that now. So let's look at actually how the flow works. Let's take our base word. Russian Cyrillic is fantastic. So many passwords in Cyrillic. So download your word list. Now the quality of your word list will of course matter here. Word lists often contain clean, some dirty entries, weird and wonderful characters, and they're not always perfect. But I downloaded a Russian word list. I then created a lookup table. Okay? Do it in your language of choice. In this case, go for upper and for lower alpha characters. And you go to your numbers and your symbols and things. Then create your translate word list using your lookup table. Again, the previous tool can do this for you. So now we're at a place where we've got some crazy stuff that doesn't look like passwords. Clearly not. Now, just for cleanliness for the demo, I got rid of anything that wasn't already an ASCII character. So anything that had basically a Russian character, I got rid of. I'm not saying you can't attack it, but I just wanted clean entries for my word list. And I had a list of thousands of passwords that looked like this, which of course you won't find in dictionaries, and no one would guess that. But they're transliterated passwords. I then threw it against Have I Been Pwned. Thousands of cracks. I was absolutely amazed that really worked, and that these were the cracked passwords. So at this point, you've now got the transliterated cracked passwords of loads of people typing in Russian passwords. And just for fun, I did the reverse lookup to convert my cracked passwords, top on there for example, back into the native Unicode, then translated that using the Google Translate API to see what the actual Russian words were typed after translation. So I thought that was really cool because, in this case, Alexandrovich wasn't hashed. That was hashed. And if you're not looking for these kinds of things, especially if you are doing tests or you have clients outside of Europe, for example, or especially going to the more eastern countries, this can really be a thing. So make sure you're sort of looking at these in your attack cycles. And it also, I won't say debunks entropy, because that's a complete lie. Entropy is good, it's fantastic, and it works, but it only works for machine-generated passwords. And when I say that, I'm generally talking about a password manager. If you're using a password manager, a well-known, robust password manager to generate your passwords, entropy works, it will calculate, it's absolutely fine. The problem is, we as humans look at a password, like the top example there, look at that and think, yeah, that's password manager generate, that looks random as hell. But that's a terrible password, absolutely terrible. So for us, only societally quantifies the randomness of how a password looks, as opposed to its actual randomness. And transliteration is a perfect example of that. Entropy assumes completely unintelligent brute force attacks, but no one does that. No one runs Markov disabled, for example, so they actually brute force A, B, C, D, E, because Hashcat would attack that way because people don't select their passwords that way. So, yeah, I'm not saying entropy is broken, of course I'm not, it works well, but it only works for machine-generated passwords. Right, let's jump into some rule optimizations. A little bit deeper into Hashcat's rule engine here. If we are attacking fast hashes in dictionary wordless mode, so that's attack mode 0, using optimized kernels, very, very important. Nearly everyone I know uses -O, optimized kernels, for the massive speed increases. You have a hard limit of 31. Okay, fine. Drop the O, you've got up to 256. But for optimized kernels, it's 31. Now, some rules, almost certainly, you'll have rules and rule operations in your rule files that introduce what are called no operations. Let's actually have a look to see what we're talking about here. So we've got two sets of rules here. We're using P rules and D rules, duplicate rules. We've taken a password of password, okay, and we're going to run this through a file called P rules, and we're going to do P1, P2, P3. Now the P rules basically duplicates the candidate. So over on this side, we've got a code on first, vanilla pass through. That's here. We've then got P1, duplicate it once. P2, duplicate the candidate twice. P3, password name, character, word. A4 is 32, above our limit. So only the vanilla candidate gets passed through, because we're now outside of the limits for an optimized kernel. Okay? Similarly, P2Z7, Z is append the last character the number of times you give it. So duplicate twice, append the last character 7 times, gives us a 31 character password. The 8th, 32. But it won't drop us back to the password, it will take us back to the last operation. So for rules that have multiple modifiers or rule operations, it won't always bomb out from the beginning. It will take the last one where it produced that no operation. Similarly, for duplicate, take a vanilla plain text of insec, duplicate it once, add 1, 2, 3, see where we're going here, duplicate, then add 1, 2, 3, so that takes us to there, then duplicate again, but it won't duplicate the vanilla word, it will duplicate the whole buffer up until this point. So that takes us to here, okay, add a final bang on the end of there, brilliant, 31 characters. Add the second bang, no, 32. So, again, we've got these instances where, and this kind of assumes you're attacking, 8 character candidates because we're going to exhaust everything beneath that. That means things like anything from P3 upwards, anything from ZO upwards that are spotted in your rule sets are affected in operations. And yeah, do you know what? For very fast hashes, you're not going to notice that, but it is going to be wasted compute effectively. So optimizing these out is going to be probably a bit better for small, concise rule sets for slower hashes. There's another interesting situation where the final length is less than the intermediate length, and this is a bit of a weird one. So it's actually the bottom of the ultimate rule, but I've done it step by step so we can see what's actually going on. We've taken a password of super secure 1 bang. The first rule is going to prepend 1, 2, 3 to it, okay? And as we're prepending in reverse order, so 3 slots in, then the 2 slots in, and the 1 slots in. Fine. We are then going to add a P4 to that. Clearly, duplicate 4 times is going to bring us way above 31 characters. That's a no-op. Fine. But what about a situation like this? Prepend 1, 2, 3, P4, then truncate the 9th character. Truncating the 9th character is within 31 characters. So that P4 in the middle is now a no-op. It's a no operation. That can be optimised out to save a cycle on that rule when running. Again, rules can help us do this. When I originally created one rule to rule them all, I did use dupe rule. It's like I'm his biggest fan. He's a fantastic guy, but he just writes really useful tools. A rule processor that can help go through existing rule sets, custom rule sets that you might have, and help achieve this kind of efficiency. Right. Iterative hashing and case sensitivity. This is where it gets a bit weird. We're going to jump into kind of data breaches and what weird things you can find now. Some systems will store iterated hashes natively. Fine. An example, a SHA-1 of a SHA-1 of a pass. Okay? Nothing unusual about that. But sometimes we get weird and wonderful instances where hashes kind of find their way into passwords and breaches. Sometimes there are cases where insecure generators have been used, or someone's gone to Stack Overflow and found someone in their infinite wisdom who says, yeah, run this bit of Python code and it will generate you super secure passwords. Sometimes it's stupidity because people think they're being clever when they're not. And for the most part, I don't know. And I don't have an answer. So let's have a look at some of these examples. Okay, so again, all from real data breaches. In the top example here from Chegg, we've actually got instances of an MD5 for password. And I should say that these are all vanilla MD5 databases, okay? These are all just plain single pass MD5 breaches. But you can see here, in the top first line, we've got a cracked password of L045, and we're using MDX find here. It's a fantastic tool, CPU cracker for large hash lists. You can see hashing it once, hashing it a second time gives us the actual value that we've cracked, okay? So, double pass MD5, 5 of them found in 27 million. Okay, that's a tiny number. There might have been some, people trying to be smart there. Do you know what I'm going to do? I'm going to MD5 my password and then paste that MD5 as the password. Okay, fine. Another breach here, 40 MD5 pass. Okay, the numbers are slowly rising. They're rising even further now. This is a bigger breach. Nearly 50 million MD5 hashes leaked. And you'll notice on this one, the clear text passwords are actually hashes. What's going on here? What fresh hell is this? There's no way 692 people... No, just no. Now, those won't be in a word list. Clearly, those hashes won't be in a word list. You won't even be able to run anything with rules to generate this. Clearly, that won't be the case. So I can't tell you how wide these got in, but looking at those, instantly I'm thinking, well, I've got to crack them. So I did, and it actually did turn out, of course, to be these passwords in the back end. So in fact, that's a triple nested MD5 if you think about it. But yeah, weird, wonderful, can't explain it, but they do exist, and some people have used them, but it could be signs of insecure generators and other things as well. And actually, the same breach, I mean, that to me screams of someone's actually used, like, referenced a blog or a tool or something, and actually used it to generate passwords, because that's hideous. That's a hideously high number for a triple MD5 nested password inside a single MD5 breach. But like I said, it does happen, and it's quite interesting to find these things in the wild. So while we're on the topic of nested hashing, we need to talk about case sensitivity. So let's take the password of password, that well-known, secure, robust value. And we are going to take the SHA-1 of that. But, as you can see here, we're going to take the lowercase SHA-1 of that, and we're going to uppercase it as well. Okay, the same password, but when we actually apply the final hash, because that's going to be a nested hash, clearly now at this point, the resulting final hash is going to be completely different, because of course we've hashed completely different characters. It's still password, and I should say that hash I believe does use lowercase hashes by default, but there are places that, that don't. What we can see is I've taken the top 20 passwords from Rocky here, and you'll see actually here, this one we're using 353E is the fourth line here, so that's the lower intermediate hash and the uppercase intermediate hash of password. That's what we're demonstrating here. So I've got the lower and upper for each one, and you can see on the right here, both on the right and left columns, and the number of occurrences that the lower and the upper hashes were found to be used. Okay, so some systems do use uppercase intermediate nesting when producing that final hash. Hashcat loves to jump around the slides of this one. So it does happen. Okay. Again, on data breaches, because it's got a bit of a rampage now to point out stupidity. I mean, unfortunate circumstances. Yeah. Chicken Man said, do you know what? You shouldn't be using a secure password, your Bitcoin address. I saw that and I was like, no, I've got to try that. Straight away found 172. I got a list of funded Bitcoin wallets. I didn't want empty ones. Straight away found 172 instances of people who are using a Bitcoin address as a password. Again, this is from Have I Been Pwned. Shocking. Yeah, I mean, don't get me wrong, that's a random string, but it's knowledge-based authentication. It's something that someone could know about you, potentially. So don't do that. And when he said that, I was like, right, I've got to go further now. What's next in my head? I used to have a bit of Ethereum. Let's try Ethereum. So I downloaded a word list. There was like 33 nearly million funded Ethereum wallets. And surprise, surprise, bang, the numbers came out on the right. And if you're looking closely, you might even see that not only have people used their Ethereum wallet address, they've even gone that extra mile. They've given it that college try. And done things like add 1, 2, 3 to the end of it, or exclamation mark, because we're humans and we love those exclamation marks and those 1, 2, 3s at the end of our passwords. So yeah, stranger things have happened, right? Yeah, I was all bets are off at this point. What else shouldn't you do? Use national identification numbers in respective countries and more. Now, I'm not for a second saying that every instance of these cracked passwords were national identification numbers. It is possible, of course, that someone could create, especially in Singapore, that's the least one, that someone could start with a capital, give 7 numbers and end in a capital. Of course, that's plausible and possible. But I was doing a sweep for multiple different passport numbers, national identification numbers, and other things. And this is what people do use social security numbers in the US a lot as their password. They shouldn't. But yeah, don't do it. Just don't do it. So we said about insecure things and random people saying this is how you can securely generate a password. Let's take the Unix epoch timestamp. Okay, let's SHA-256 that, base 64 it, and cut off at 32 characters because why not? So yeah, Chicken Man found it, but I wanted to try it a little bit different. Now I was lazy and I only went as far back as 2015, and then I tried SHA-1 because I thought SHA-256 fine. Let's just see if there's anyone out there who's decided or seen a Stack Overflow post who's taken the Unix epoch, SHA-1'd it, and then truncated at 32, and surprise, surprise, within 20 seconds I got my first hit. Here it is. So I worked it back, and you can see where the highlighted truncation occurs, and there's what the value is. So, again, don't do it. Science. Let's talk about science. I was on by this point, the coffee was flowing, the night was young, and I was clear. I went through crypto, I went through everything on my own science, because why not? Googled list of every element and compound I could find the chemical formulas, downloaded that, ran it through with prints from a minimum element count of 2, but an overarching minimum length of 10, because if it was any lower than that, I felt you're moving slowly into the realms of plausible brute forcing, maybe. Ran that through, phone passwords. I killed it at 12 hours because it was going quite slowly. I had 121 cracks, and I was 313 billion guesses in by that point. But look at them. I mean, Am I saying here categorically that every one of those passwords came from a scientist of some description? No. Of course I'm not. But seriously, if there is a Nobel Prize for compound discoveries and passwords, I should be awarded it, in my opinion. That's why I will take nominations. But yeah, some crazy, what appear to be chemical formulas coming out, because why not? But the rampage didn't stop. I went straight to Stack Overflow and started Googling for people thinking they were being clever. And it didn't take long. I love linguistics. In my approach, I create memorable pseudo-passwords with high levels of entropy by doing this. What this is alternating consonants and vowels, starting with a capital consonant for 10, with an optional number, because the optional number will make you secure. But we've already established entropy is a lie when it comes to human-generated passwords, and this is a human-generated password. Now, that's not the worst entropy in the world, but it's not enough either, okay? Not enough. Also, yes, true, it might not be susceptible to a traditional dictionary attack, but it is susceptible to trivial attacks, as we can quickly find and see. And that just makes me feel sick. Someone saying short passwords are secure and decent strength. There is nothing strong about a short password. That's the end of it. So I literally chat GPT to Python script, because that's how I roll, to generate as much as I could, because I'm a terrible developer. And yeah, straight away. Again, could these be plausibly generated outside of that? Yeah, I'm not saying it's impossible. But when you've got a format that thousands and thousands of people are looking at and might take away and use, it's not hard to see that you might be able to get these quick wins. Okay, on to the last bit then. Automating non-distributed workflows. So this is a tool I released last month, I think. I can't remember. Called Hash Catalyst, and it is just a wrapper, nothing more. I'm not a clever developer. This is just for helping automate the heavy lifting cycles. If you don't have massive company rigs that run 24/7, if you don't have hash topless overlays over multiple data centers, and we do have a company one, but if you, like me for a long time, have your laptop going, I don't know, and you're a couple of hours, you're about to go to bed, and you start an attack, and the attack's going to finish in 2 or 3 hours. I'm going to go to bed. But all that dead time overnight, that's being wasted while it could be cracking. Hash Catalyst to the rescue. And I will try and wing a live demo in a second as well, because, recordings are for wimps. Windows batch file, Linux bash script, flexible attack chaining. It does have some more enhanced word list generation stuff as well for people who aren't using Expander and CutB to augment their word lists and their pop files. You really should be. It logs everything it does, in case that actually Hashcat has an error underneath. And yeah, basically, you can see the different types of attacks we've got here. What you'll want is number 16. Hit 16, plug in the numbers of what you want in the order you want it, press go, and then leave it, depending on what you've entered, possibly forever. What you need to do, regardless of the Windows or the Linux variant, is just go into the file, and you just need to set these file paths. That's all you need to do, okay? Any developers in the room are going to be screaming this horrible code, and fine. There's going to be better ways to augment this, but the way I've split it out is we've got individual rule files, if you want just single rule attacks. We've got a rule folder and a word list folder, so there are attacks whereby if you put multiple word lists that need to be a .txt extension, Hashcat will go through and cycle each word list in there with your rules. Similarly, one or multiple word lists with every rule file in a rule folder. So depending on how many rules you've got and how many word lists you've got, this could go on for quite a while. And it also includes rlite, which is a fantastic binary for sorting and deduplication. The reason I love rlite is because whilst sort-u, unique, etc. are fine, A, they don't really get all edge cases. B, in Windows, sorts.exe does have an undocumented unique switch, but it's terrible, useless, and falls over for anything that falls outside of ASCII. And rlite is just brilliant. It is, I believe, memory dependent. So if you're trying to sort a 64 gig word list, but you've got 32 gigs of RAM, that's not going to work. But it's generally a lot faster, a lot better, and a lot easier. And this is how it logs. So every entry is timestamped, the attack you're performing, and the full expanded Hashcat command line to all the paths of all the things you're doing. And like I said, let's see if we can... Here's one I prepared earlier. I don't have a pot file yet, and I don't have an attack log yet, so let's start up Hash Catalyst. Right, okay, we can see here, just what I've demoed on the screen, we're going to want 16. I should also say that you can show your current paths, just so you can see where your current paths are, if you've got something wrong or you've done something and incorrect. Show cracked passwords. Nothing to the show at the moment because we've not cracked any passwords. So we're going to take option 16. Enter your attack chain, and let's say you want a hybrid word list number 2 with then a word list with rules, and then 14, a word list with random rules. So 2, 6, and 14. 2, 6, 14. And then you can see, and I think I've done a good job of stripping all profanity out of here, because I did mark this talk as PG, so I'm building the sweat. You can see it's going to go through, hashcats cracking on the left there. This is our pot 5 in real time. Every time it starts a new attack, it's then going to log. And I probably shouldn't have picked one with random rule generation at the end, because this could now go on for as long as it generates random rules. All of the rule-based attacks use loopback. Loopback is fantastic. If you're not using loopback already, please do. What that does is, from a single hashcat session, if you've cracked 1,000 hashes with a rule, it will then take those founds and reinsert them into the chain to reapply the rules over the top of them again. And it will just keep going and remangling your founds each time until it can't find any more. So I think we're already on the hashcat induction loops. This is now the last attack. And if I'm lucky, it might quit. If I'm not, oh, there we go, quit. If not, it's going to keep going. So now at this point, what we can do is we can say 29, show us our cracked passwords. Here they are. I don't scroll too high there. Oh, steelcon passwords. Okay, fine. I think I've lent in the keyboard by mistake there. And also at this point, what we can do is we can look at augmenting our word lists. So as I mentioned, we've got here lists folder. Right, let's create a pot file word list. So a pot file word list, again, something we should all be doing, is not using RockQ anymore, or our top 100 or whatever it is, and using our cracked passwords as the word list. So we can do that with option 21, create pot file founds list. 21. It's now created that in the folder I specified as my word list directory, called pot file text. There it is. If I open that up, we can see we've got all the cracked passwords that we've just got. Fine, fantastic. We can now use that as a word list. But what we can also do is we can expand them, and we can use cut B over them. So expander, which by default, where are we? 22, yeah. There we go. It's expanded them. It's already used rlite to dedupe it, and it's got expanded potfile.txt, which is now here as well. 26 kilobytes, a lot more. And you can see this has now expanded every one of our password candidates. And expander splits and mutates all of our passwords into segments. Cut B does a similar but distinctly different thing. By default, expander is supplied with a maximum length of 4, so I highly encourage you to edit the C code to 8, maybe 10 if you're feeling brave, and recompile to get more mileage. But you'd be amazed that when you're using things like this in A1 attacks with itself and other things, the type of mileage you can get from that as well. So have imaginative fun with your word lists. We released for free, we're previously commercial with Black Hills Information Security, but I think it was in 2022, we released Password Cracking 101. If you're not already sick of the sound of my voice, and you should be, you can have 4 more hours of it. I know, right? Over 15 YouTube videos. There's a VM, it's a VirtualBox OVA formatted VM. Download that. It does work on VMware and other things, but I won't lie, I'm not going to troubleshoot too many hardware issues. It works, okay? It's pre-built with 15 hands-on questions and answers already in there. And it starts from the very basic, and it gets more and more progressively deeper until you get into hell around about here. It does cover foreign language, emojis, and other things, and it does do some attack analysis as well at the end. If you're still thirsty for more, we released a CTF in 2018 where there was a crypto prize. The $100 of ETH was swiped in 4 hours, but the challenge is still there, so feel free to have some fun if you want. And yeah, that wraps it up. And I'll answer your first question for you. No, I didn't forget Hashcat. Hashcat likes to be on every slide, but that does wrap it up. Hopefully you enjoyed that. Thanks very much for attending once again. Obviously, I'm happy to speak to any more questions afterwards.